Okay, welcome to our video on rates of reaction. In previous videos I've described chemistry as being like playing with Lego. The individual Lego block is like an atom. You can break models apart and join them together in a different configuration. The models we start with are the reactants, and the ones that we make are the products. So reactant first, and the reactants turn into the products. This rearrangement of Lego blocks is a chemical reaction. And some of them are slow, like rusting, that's the oxidation of metals, and some are fast, like an explosion, where you get a rapid production of gas. So, how do you measure how fast a reaction is happening? Here we've got a reaction where a gas is produced, and if we use a conical flask, you can measure the mass lost, or the volume of gas produced in a minute. When we react sodium thiosulfate with hydrochloric acid, you get an insoluble solid formed. And this makes the solution appear cloudy. It's called a precipitate. A common way of testing the rate of reaction is to draw a cross on a piece of paper and put the flask over this cross. You combine the reactants together and you look down through the solution, through this liquid, and you time how long it takes for the cross to disappear, at the point where you can't see that cross anymore. Stop the stopwatch, and there you go. That's a nice way of measuring the rate of reaction. Now, for a chemical reaction to take place, the particles must collide with enough energy for the reaction to be successful. They actually have to bang together with enough energy. If they just sort of glance off of each other slowly and gently, there is no reaction to be had. The graph that you can see here shows that energy has to be put in before the reaction to take place, and then when the reaction takes place, you get the rest of the energy out. The little hill on the graph is known as the activation energy barrier. And if particles don't collide with enough energy, the activation energy barrier is not passed and no reaction can take place. The more successful collisions per second, the more successful collisions that you have per second, the faster the reaction is going to be. So, how do we get more collisions per second? Well, firstly, concentration. You can think of concentration as the number of particles in a given volume. These particles are bouncing around and colliding with each other. So if we increase the number of particles, we get more collisions per second, and therefore a higher rate of reaction. You can see here that you get more collisions with a higher concentration of reactant. You get the same effect if you increase the pressure. In a gas, an increase in pressure squeezes those particles together into a smaller volume, so they collide more, just like with a higher concentration. So, higher pressure equals faster reaction. In, for example, the Haber process, which is a chemical reaction used to make ammonium nitrate fertilizer, they use 200 atmospheres of pressure. So this is used in industry to increase the rate of reaction. If we increase the temperature, the particles have more kinetic energy, so they move around faster. Not only does this mean you get more collisions per second, but it also means that the collisions that you do get are more likely to be successful. That the smashing together of these particles takes place with more energy, and so you're more likely to breach that activation energy barrier. So, higher temperature, particles move faster, which gives you more collisions per second, and the collisions that do happen have more energy. This graph shows the hotter conditions, the faster the reaction occurs. But, given time, the same amount of produce is formed. The same amount of product is formed. It's just that one does it slower than the other. In this diagram, we have 28 red particles on the outside, and they're the only ones that are available for the reaction to happen. All the others are trapped inside the solid where no collision can take place. So this is the surface area. These 28 red particles on the outside, they are on the surface. If we chop this solid into smaller pieces, we still have the same volume. There are still 60 atoms, but we have a larger surface area exposed. We now have 36 particles available for collision. So, by chopping something in half, we've kept the volume the same, but we've increased the surface area, and that means there can be more collisions, and this means the rate of reaction is faster. Something you might consider to be totally unreactive can explode. It can seem to react very fast. There have been explosions caused by custard powder or flour or just things that you wouldn't imagine could cause an explosion in the first place. But because they've got such a large surface area, they can react quite quickly. Right, finally, let's talk about catalysts. You've seen a graph like this, and we discussed earlier that for a reaction to happen, the activation energy barrier must be reached. A catalyst works by reducing this barrier, and this makes a reaction more likely to occur. So catalysts speed up chemical reactions. Respiration, which happens in all the cells of our body and provides the energy for life, is a chemical reaction. It's a biological chemical reaction, if you like. It's a chemical reaction that is needed for life to exist. And it's controlled by biological catalysts. It's controlled by enzymes. Enzymes work by lowering that activation energy barrier. And without those biological catalysts, there would be no life on Earth. So, these are the factors that affect rates of reaction. If this video has been any help, please hit the like button and feel free to leave a comment. Let me know how I can improve these videos. Any feedback is more than welcome. Thank you very much for watching.